Okay, so ladies and gentlemen, what I need from you is that because it's actually not easy, it's almost like when I view videos on here, we have that situation where we have to, get one of the students to view the video so you guys can listen and so on and so forth. So I'm not going to do that. And also, for some reason today, when I share my screen, it's slightly difficult. So I advise that please download the lecture for the lecture, which is for this week. So that, but I'll tell you what slide I'm on. So as I get along, just make notes of whatever is not on the slide. Instead of just going back and forth in trying to figure out the screen thing. We don't have much time. So without wasting any time, there's about over 10 people, so let's continue. All right, so the last lecture we ended by looking at the practical implications of deformation. But before we carry on, I just want to make sure that everybody can hear me. If you can, please give me a thumbs up in the chat. If you're logged in here, just give me a thumbs up, please. I know that I've muted everyone, but you can still chat. Can y'all hear me? Great, Brown, thank you. Okay, Clausen, I see you. Thank you, thank you, thank you. Thank you, guys. All right, so we are on slide 26. So if you download, if you have a copy of the lecture, we are on slide 20. Actually, we are on slide, yes, we're on slide 26, where we're looking at the theoretical aspects of deformation of hardened concrete. But prior to that, we had a look at load-independent deformations. We had a look at the adverse effects. We also had a look at control effect of deformation. So now we're going to look at the theoretical aspects of deformation. Now, deformation in concrete is not something easy. It's relatively complex, and as such, if you look at what concrete is made of, the various ingredients, we know that if there's any deformation, it will happen within the cement paste itself. Why? Because aggregates are stiffer and aggregates are harder. So aggregates do maintain their dimensional stability even in deformation. If you look at the cube test or the test for the strength of concrete, normally if there's any failure, the failure happens between the aggregate paste interface. So at that point where the aggregate and the paste stick together, so it's in the cement paste that any deformations occur. All right, if you look on slide 27, there's a picture of deformation of hardened concrete. You can see that the pavement has various cracks. It's quite unsightly. I mean, as you walk around, you might see that. I haven't, even on campus, if you pay much attention, you'll find some of these unsightly hardened concrete deformations. Even in your neighborhoods, apparently now level 4, we can walk around a bit. So as you run around, just open your eyes and see if you can pick up any deformations of any of the hardened concrete that you come across. You can take photos and maybe share it with us. Slide 28, it's an individual that is he's cutting joints in. So there's a nice concrete apron around the pool. So in order to ensure that there's some sort of facilitation for expansion and so on, he's cutting some joints, expansion joints with that machine. I'm sure for those of you that have worked on site and are well experienced, you have come across that before. All right, so when we look at the theoretical aspect of concrete, we're looking at slide 29, we look at load-induced deformations. Now, as explained earlier in the previous lecture, we looked at elastic deformations, and normally when stress is applied to any structure, the stress results in a strain of the structure. Now, if that stress is removed, then the structure of the material sometimes can recover or get back to its original shape. And if this happens, that kind of deformation is known as an elastic deformation. It's just as simple as an elastic band. You stretch it, once you stretch it, it changes size, becomes relatively longer, and then as you reduce it or you release the tension, it kind of like bounces back to normal. But if you keep on doing it, eventually it will lose its elasticity. It does goes back to normal, but it at a point does not recover as much. All right, then we going to have a look at creep. Now, creep is time dependent, which means that as over time, please switch off your microphone. Nothing has changed with the rules, guys. So if we look at creep, I've muted everyone, but for some reason, anyway, so let's get back to it. So we're looking at creep. So in defining creep, we know that creep is time dependent. So if you increase strain on any object, creep occurs, especially when the stress is sustained over time. So the longer the stress is, then of course creep occurs. So having some sort of idea with regards to elastic deformation and creep is ideal for our purpose. If you look on page 102 and page 104, it should be there. I do believe, I don't even have a textbook, guys. My textbook is on campus. I was also not thinking would be locked out for this long. However, these are based on the old book that I have. So if the pages are the same, then it's great. If not, then please it should be a couple of pages ahead or 1 or 2 pages behind. All right. So if we look at load independent deformations, we talked about dry shrinkage. Now we're going to look at factors that affect dry shrinkage. We have the water cement ratio. We have the water content. We have paste content. We also have environmental conditions. We have time. We have cement type, admixtures. I'm on slide 30. We have aggregate types, member shape, and size. Now, when we talk about paste content, a high paste content versus the aggregate content, normally you have a larger shrinkage. So the more concentrated the paste is in terms of cement paste, the greater the shrinkage of that particular hardened concrete structure. If we look at water content, this is very important because water content is directly water content directly influences hardened concrete or the deformation thereof. So that leads us also back to the water cement ratio. You can't just add water into your mix because the more water you add into it in your fresh concrete in its hardened state, then no, of course you have an issue with the strength of the concrete, and if it does not meet the strength that's specified, then you may have obviously various problems. But at the same time, also if one ingredient is added, is increased over another, then again you still have some sort of influence or adverse influence on it in its hardened state. So whatever we do in the fresh state of concrete, it normally has an influence in the hardened state. When we look at time, normally we look at deformation. It happens between about the first 6 months of any structure. Yeah, but if you're going to see any kind of deformation, you should see it, at least within the first half of the year after the structure has been built. All right. Admixtures, certain admixtures have various properties. We've already touched on admixtures. So depending on what admixture you use, is vitally important to assess the impact of that particular admixture in terms of a hardened concrete, or in the curing process where the concrete cures, because some admixtures may have some sort of influence on how much moisture is lost. And as a result, if the concrete loses moisture excessively, then we also have some sort of influence with regards to shrinkage. And then also we look at the member shape and size. If we're looking at the size of the hardened concrete, that also has an influence. I mean, if you have a beam and the beam is very slender and the beam is not suitable for the load that is imposed on it, definitely the beam will deform in one way or another if you have a column as well. So these all have to be designed by an engineer, and as such, I mean, they are well qualified to do that job. All right, let's look at slide 31, where we're looking at load independent deformations. We have joints, dry shrinkage, we have the outflow of moisture from the concrete. All right, so when we look at joints, normally joints get wider, and as a result, they should be designed to accommodate some sort of increase in their size should deformations occur. You also have other materials. We need to take into account that certain materials also shrink. We should also bear in mind that if you look at something like sand, right, when water or when water is added to sand, it actually increases in its size. That's the reason why when we mix in concrete, ideally we kind of wet the sand a little bit, so that the sand does not absorb, or the fine aggregate does not absorb as much water. Otherwise, then we kind of like miss our water cement ratio in terms of mixing the concrete. Okay, remind me. Okay, I am recording. Switch off your mic. Okay, great. I was just checking to see if there are any questions. All right, when we look at cracking, cracking is something that occurs in hardened concrete, and mostly designers minimize minimize cracks by obviously including expansion joints or construction joints. It will make sense that if the concrete is going to crack, then at least it will crack along the side of the joints, but it's not always the case that it does so. Sometimes also, if you have something like grouting, that also results into a loss of pre-stressing forces, which also now contribute to dry shrinkage. When we look at repairs, of course, hardened concrete can be repaired. We have specialized grouting that can be used to repair it. If you have a concrete surface like floor slab where you have some cracks or whatever, this can be obviously repaired. But in minimum, I mean, you have some cracks that are so deep that it affects the structural integrity. But in most cases, depending on the size of the cracks, these can also be repaired. And then if we look at the bonding between concrete and the rebar, now it's very important that the bars, the reinforcement and the concrete bond well together, because if they don't bond well together, it is at that interface that it will break, right, or it will crack. So there needs to be adequate bonding. And that is the reason why reinforcement should not just should be free from oils and so on and so forth. You don't just dump them on site. They shouldn't be rusted and things like that. Otherwise, it affects the properties of the hardened concrete when, of course, it has hardened. And then, of course, if we look at deflections normally looking at columns and things like that. So columns deflect based on the loads that are imposed on them. If the columns are not designed to support or suitably designed for the loads imposed on them, they will obviously then deflect. All right. Now we're going to have a look at, so this brings us to the end of chapter 9, all right, looking at hardened concrete. But in your time, since I don't want to waste time at all on this in this lecture, I want you to watch the videos that were loaded for this particular lecture for the week. So I think last week we watched one, or the last time we had a lecture we watched one. So basically there's the one types of cracks and beams. I want you to have a look at that, watch it in your own time. Bending and buckling, very important, because these are all types of deformations. We have the water cement ratio in concrete strength and why it is important. We've been talking about this forever. Then we have creep in concrete. So please watch all of these. I don't want us to watch it because then we'll just be wasting a bit of time. So watch it in your own, but before obviously the next week's lecture. Okay, now chapter 10 deals with the durability of hardened concrete, right? Now, the reason why chapter 8, 9, and 10 is obviously put together is because the one influences the other. The strength of the concrete has an influence on whether it will deform or not. The deformation will have an influence whether this concrete is durable or not, right? But the strength of hardened concrete is influenced by the properties of the fresh concrete. So from fresh concrete, whatever you do there affects the strength of it. Whatever you do there affects the deformation of it. Whatever you do there affects the durability. So you need to see it as a link. One leads to the other, having that understanding. All right, so in this chapter, we're going to have a look at durability of hardened concrete. Just, a brief introduction to it. We'll have modern durability design. We have factors affecting concrete properties, influencing durability, the mechanisms of deterioration. There are various means or various ways in which concrete deteriorates. All right, we're going to have a look at that. And then we're going to also look at performance-based durability testings, and very much ones that are specific to our South African context. Right, so if we look at durability of hardened concrete, right, durability of any hardened concrete is the ability of that particular concrete to withstand the design environment over the design life. So if you design a structure, the structure should be designed in such a way that it should withstand all the environmental impacts, all the environmental conditions, all the service. It should be able to service the purpose for which the structure was made over its lifespan. You build a bridge. That bridge should be able to service, or it should be used for what it was made for. It should, if the bridge was designed for 100 years, right, it should last 100 years and still service whatever need it was made for. Now, in mentioning that, though there are repairs to any structure, to anything, but there shouldn't be major repairs in such a way that, geez, it's something so significant. There are repairs here and there. I mean, even if you look at road construction, there are small repairs here and there, but seldom do you find a road or an entire bridge being condemned and a new one being built, unless there's something structurally wrong with it. I don't know if you remember a couple of years ago, between Port Elizabeth and Grahamstown, a piece of the road was washed away. I think we had some heavy rains and something like that. So they had to make a bypass. So in a situation like that, of course, the entire soil, the soil underneath that road was washed away. So the alternative was a bypass to it up until they could actually fix it. So something like that is inevitable, but ideally, any hardened concrete should be durable. It should be obviously built or designed to withstand the environmental conditions, and then of course the design life without losing its serviceability, as well as major repairs. You don't want to excessively just repair things. There should be repairs, but it should be, within some sort of reasonable parameters. All right. Now, when we look at concrete durability, we know that it relates to the performance of it, but the durability of concrete does not necessarily come from the intrinsic factors of concrete. So it is not necessarily due to the intrinsic factors or the intrinsic properties. If you look at the intrinsic properties of concrete, it's the properties within the inside of the concrete. Now, the reason why I say that is that we can mix a concrete and build a structure. Here in South Africa, that particular structure may not be suitable for a European context because there's environmental conditions that are different, their weather is different, and so on and so forth. So if concrete is durable in one particular environment, it may not necessarily be durable in another. So looking at the consequences of inadequate durability, we have loss of serviceability, not that particular structure not being able to service or to provide a service of which it was designed for. Unsightly appearances. I mean, nobody wants a concrete structure, be it a floor or whatever it is, to have unsightly appearance like cracks or, just funny, it looks unsightly. You build a structure and then you don't even want to live in it anymore because it does not look too nice. Or you don't want to use it because it does not look too nice, yet you've wasted so much money on it. If the concrete is not durable, then there's a risk of danger to people. There's a risk of danger to property. If you have structures collapse for whatever reason, or we have bridges that fail, or you have floor slabs that just cave in, that kind of thing. The people should not be injured in it, and then also property should not be damaged. Now, if the concrete lacks durability, then of course there will forever be repairs. You will repair that structure up until you decide to just rebuild it. All right. So in the life cycle of that structure, in 100 years of this bridge or 100 years of this road or whatever it is that you're building, you're going to have extensive repairs just to bring it up to scratch. So the best thing is actually to design it properly, design it with integrity, so you can just minimize all of these things. If it's designed well, then the maintenance aren't that major. All right. And then, any structure undergoes maintenance, but you don't want to be excessively repairing or maintaining it. And then, if concrete structures aren't durable, what happens is that, the general public then has a poor perception of concrete as a material. Nowadays, there's a trend or a move towards more sustainable materials, such as wood for building. Even in foreign countries, you have bridges that are being made of wood, and they are quite durable, they are quite strong, and they meet all the requirements. But in our African context, we have this perception that concrete is strong. We know it is strong, right? But the more concrete structures fail, the more concrete structures fail to be durable, people's perceptions, ideologies, and just general feeling about concrete will become negative, right? And we don't want to have that. Right, if you look at slide number 36, there's some pictures of concrete that is not durable, or, just showing you what happens to concrete when durability is questioned, or there's some sort of question mark to the durability of the concrete. You can see in the second picture, there's even some vegetation growing in the cracks. Those are very big cracks. In something like this, I would think this should all be removed and used for aggregates or whatever. The one on the left-hand side is a bridge, and it's quite unsightly. It doesn't look that beautiful, but you can see that it requires some sort of maintenance in there. So that is on slide 36, and it's just showing some pictures of what, a concrete or structures that don't have optimum durability. Okay, so the next slide, which is slide 37, also you can see that the structure, there's a bit of spalling. As you can see, you can even see the reinforcements. I think you can all see that on page 30, slide 37. The rebars are showing. The next one is a structure, so it's changed color slightly. But these things happen over time, so it's not something that happens immediately. Over time it happens, but if we design our structures properly, then we can reduce these kind of what do you call these, concrete, should I say, problems that require repairs. All right. Let me just see. How do we ensure that concrete is durable? All right, we ensure the concrete is durable, because I have a question. We ensure the concrete is durable. Please repeat page numbers. Oh, sorry, I didn't see that. I think it was page 10. Hold on. Klassen, are you referring to the slides, or are you referring to the page numbers in the textbook? Can you please specify? All right, while you do that, let me answer Odwa. Odwa, textbook. All right, textbook, it's on page, hold on for me. So textbook, you go to chapter 10, sorry. But in chapter 9, I think it was page 110. There was one on page 102, page 104, all the way to page 110. I think those were the pages that I was looking at. And then the next one, if we talk about the durability of hardened concrete, I think it's on page 115 or so. But you should be finding it as the chapters go on. All right, Odwa's question. All right, you're welcome. Odwa, how do we ensure the concrete is durable? All right, we ensure the concrete is durable by, firstly, it has to be well designed. Okay, I'll answer the question now. If you look at, in order to prevent such things, it's got to be designed by a competent, qualified person. So remember, we're not here to go and design structures. We are building, okay? First, it will be designed by a competent person, by an engineer who designs it based on specifications. Then, as builders, we've got to build it right. There's a big difference between an experienced, competent contractor and a fly-by-night contractor, right? So workmanship, as well as the structural integrity in terms of design is very important. So the design, the economy, or an economic design that makes sense, economic design that suits the specifications, and then the person that actually builds it also has to make sure that they're building it to the spec. There's a big difference between an engineer designing a structure with the various specifications and a contractor doing it and building it according to the specifications. There are so many stories whereby contractors just don't follow, or contractors just don't build according to spec, and then you will have a situation where structures fail. Or we have engineers that are not experienced, all right, that design structures, and then of course you have all of these model problems. I don't know if that answers your question, Odwa. The next question is, if you can give me a thumbs up, I'll be more than happy. In section like slide 37, how would you go about repairing the structure? Okay. Let's go to slide 37. All right, so in this, what happens here is that, of course, the surface would be removed. Any rust, if it can be removed, normally it would be the surface of the structure will be removed. A bonding agent will be applied, and then of course a fresh concrete will be applied to it. If you see, I don't know, for those of you that don't know if you travel, but along the beach, the beaches, it's a apartment block. They constantly do repairs because of the effect of the sea, all right, and all the and the chloride attack on the structure. So it's a concrete structure. So as such, there's a little bit of spoiling. So they constantly remove the surface and then they patch up. They obviously cover up with new reinforcement. Also, getting to the boardwalk just across, just as you drive slightly further, you'll see that a number of the apartment blocks undergo these kind of maintenance, and it's only because salt water attacks reinforcement. But in this case, there's been a little bit of spoiling, so they're removing the surface of the concrete structure. All right, the reinforcement will be treated a bit, a little bit of bonding agent will be done, and then fresh concrete will be applied to it, and then it obviously be allowed to cure. Okay. Okay, got that. Got that question. Luyanda, I just answered your question. Okay. All right, so next we're going to look at modern durability design and specifications. Right. Now, when we look at modern durability design and specifications, this is on slide 40, okay? We are looking at designing to suit the environmental conditions. We're looking at the structural interaction, including service stresses and serviceability, how the structure interacts with the service it is expected to perform. We're looking at the quality of construction. This is what I've just explained to Odwa now. Quality of the construction is important, and I'm sure most of the guys that are on site and are working will agree with me. If the quality lacks on site, definitely the durability of that particular structure is questionable. We look at the durability in terms of the design, optimum durability. So whatever is being designed, is it being designed to meet a certain level of durability, or is it just being designed for design's sake? As an example, when you design foundations, those foundations should last as long as the building lasts. Okay. Now, if you design foundations with whatever poor materials or low strength, or cement, or even if you go as far as using masonry cement, that kind of thing, you will definitely have a problem with the durability. So it's very important that when we design for optimum durability, and this normally comes from the engineer. All right, so there's a comment from Clausen. Thank you. He says Sika, ABE, and Hilti has purpose-made concrete repair mortars and products which cost for repairing the exposed rebar. So these are these are examples of materials that are used for fixing coats. Thank you. For fixing the exposed rebar. All right, so that still answers the question that was asked by Luyanda. Okay. All right. If you look on slide 41, thank you so much, guys, for your contribution. If you want to contribute, guys, please just type it in the text. We're supposed to be interacting. If you look on slide 41, we're looking at a picture that looks at quality over time. Now, if you look at A, you look at B, you look at C. If you look at A, quality starts and then it reduces. It goes all the way to the minimum acceptable quality. Then it increases. It goes all the way. So we have situations whereby we have a structure. It's of good quality. Then it reduces to the bare minimum. There's some sort of repairs that occurs. Okay, so the quality increases. Then over time, it decreases and on it goes. So this illustrates what happens to hardened concrete over time in terms of durability. Well, at the end of the day, it's not possible that you'll build a structure that will never be um, repaired or maintained in any way. It will be, but at least there should be some decent time between repairs or between major repairs. We wouldn't want a situation whereby now every now and again you're repairing something. These things cost money. It's not cheap. So that figure is for, figure 10.1 is just for you to understand it. I don't expect you to learn that or label it at all. Let's look at factors affecting concrete durability. That's the next one under the section. Now, slide 43, we're looking at factors affecting concrete. Ladies and gentlemen, this slide is very important. You need to be able to understand everything in here. As a matter of fact, if you understand this, you've kind of like got this chapter. So if we look at concrete durability, we have it splits into two parts. We have the concrete system itself, and then we have which constitutes the intrinsic factors, the factors inside of the concrete, the extrinsic factors, the factors outside of the concrete, so outside of the structure. So we're looking at what is in the environment. Then we look at the aggressiveness of the exposure environment. So we look at what is in the environment that affects the durability of concrete. So we have the physical attack, physically, what physically happens to the concrete that it deteriorates. And then we have the chemical attack, what happens chemically within nature that affects the durability of concrete. So if we look at the intrinsic factors, we have the cement type, design mix proportions, water cement ratio, aggregates, the whole lot inside of the concrete. When we look at external or extrinsic factors, we're looking at production, we're looking at concrete processes, the process or construction process rather, the process of building the structure, experience versus a novice. Having a contractor with 10, 15, whatever years experience and having a contractor with 1 year experience, that makes a difference. We look at curing, we look at temperature and moisture in the environment. Okay, then we look at early age temperature history. Now, if you look at the extrinsic factors, I'm not sure if you guys can see it very well on your slide because of the logo, but under the extrinsic factors, the first one is production and or construction processes. Example, mixing, placing, and consolidation. The next one is curing, which is temperature and moisture in the environment. Then the last one is early age temperature history. So these form part of the extrinsic factors. Now, I'm not sure if you guys can see it on the slide because of the Nelson Mandela logo right at the bottom left corner, but I've just explained that, so maybe you can just write it down. Okay, now let's have a look at the aggressiveness or the aggressiveness of the exposure in the environment. So we have physical attack and we have chemical attack. Physically, we have abrasion, erosion, cavitation. We're going to go through every single one of them. We have freezing, we have thaw. Thaw is the same as melting. We have salt crystallization. We have effects of cracking due to loading or thermal effects. We have the chemical attack. We're looking at the nature and the concentration of aggressive agents. We're looking at the internal chemical instability. We're looking at the effects of temperature, especially in humidity conditions. So looking at all of this, these affect durability. These should be well understood. You should be able to identify them. You should be able to pick them out. You should be able to distinguish between the intrinsic and extrinsic factors affecting durability. You should be able to distinguish between the physical attack and the chemical attack affecting durability. So this table, or rather this slide, is vitally important. All right. Now, when we look at durability, I think the next point under this is looking at the concrete properties influencing durability. So what properties what properties within concrete affect durability. Now we talk about transport properties. We talk about mechanical and physical properties. We talk about chemical properties. When I'm talking about transport, I don't mean transporting vehicles. I'm talking about inside the properties, how the materials move, how the materials, are moved within the concrete itself. So we're going to have a look at each and every one. Now, when we look at transport properties, we look at the ease with which fluids or ions can move through the concrete in its microstructure. So if you take a concrete, you put under a microscope, how are the ions, how are the fluids, how are they moving inside the structure? Of course, if you don't do such an experiment, you're not going to see it. But what I would advise is that for better understanding, maybe just get onto YouTube and try and see if you can find transport properties. Maybe one or two of the videos will have something under microscope where you can see. If you can find something like that, please share it with the rest of the group. Like I said, I'm trying to avoid doing everything myself. Yeah. Okay, let me just hold on and see if I have any questions. Okay, no questions. All right. Now, under transport properties, we have permeation, we have absorption, we have diffusion, we have migration. So permeation deals with the movement of fluids through saturated pores under externally applied pressure. Okay, so how the fluids move in a structure. When we look at absorption, we're looking at how fluid is drawn into the pores. Fluid is drawn into the structure, be it through capillary action or whatever the case is. How is that concrete structure absorbing water into it, absorbing fluid, absorbing rain, whatever the case is? When we look at diffusion, we look at movement of liquids and gases through what? Materials due to a concentration of gradients. So if you lock yourself up in a room and then you spray something, how that spray moves into other places or into other rooms, that is known as diffusion. So you're looking at the movement of gases and ions, liquids, and so on, due to concentration, of it being concentrated. If you remember from Fees Must Fall, when we had the tear gas and so on situation. So tear gas would be, obviously, the police would use tear gas to disperse, but then the gas will diffuse through windows and openings, and then all of a sudden the entire M block was filled with tear gas, even though the tear gas was obviously released, a couple of meters far away from the M block. Then we look at migration. Migration deals with the movement of ions in a solution under electrical potential energy. So for our purpose, we need to remember permeation, absorption, diffusion, and migration. All right. For chemical and physical properties, we look at strength, density, and stiffness. These are very much specified because the specification of the engineer will give us the strength. The mix will tell us how, the stiffness of it or how dense the particular structure will be. So when it comes to the chemical and the physical properties, these are very much things that are specified. So if you follow the specifications, then of course you meet these properties. If you look at the chemical properties, we're looking at cement blends, some blends that increase concrete pores. So certain cements with certain blends of cement increase the pores. So there is always some sort of a chemical, some sort of a reaction within the concrete. But we're going to look at each of these in a broader detail in our next lecture. I think we should stop here for today. What do you think? So I'm stopping on slide 45 because I need you to, what I'll do is that I'll try and add up a couple of videos between now and the next lecture, especially on durability and things like that, so you can watch. But if that's okay with you, I think I've been talking for more than an hour already. Then we can Alex, more than happy to end now. I see that with your arm. Okay. No, we'll carry on. We'll carry on Wednesday, I think is the next lecture. So just expect an invitation, and then of course accept it. By the way, the videos will all be on this platform under meetings. So if you go to meetings, you can see videos and you can always watch them and do whatever it is you want with them. But yeah, please just use it to your advantage. Okay. Class rep, the test, did we say the 14th or the 15th? Because I think I said the 14th, the Thursday.
You said the 14th then.
Yeah, 14th. Okay, because I got an email from somebody asking that it's the 15th, which was not. I don't even know. So it is the 14th. The reason why it's on the 14th, because the 14th we have a lecture, so we'll do it during our lecture time. Yeah, so if there are no more questions, guys, I'll see you on Wednesday at whatever time it is that we have the lecture.
Ma'am?
Yes?
How's this test going to work?
The test?
Yeah.
Multiple choice.
Okay.
Okay, so I know there's an issue with connectivity and things like that, guys. Right now, the test is multiple choice. We'll see. Let's wait and see by next week what happens. If the connectivity does not work out, I will give an assignment. I think either I'll give an assignment or we do a test. The way things are going, I might just give an assignment because it defeats the purpose if students have data, but the cell phone network is bad. Even for me at home, I use a cell C router, and I took about 30 minutes just to connect to Teams today. So I do understand the connectivity thing. I really do. But if we don't get to write the test, we'll have to come up with another plan. Okay. Remember, this is a blended learning thing. So they are, we can explore whatever options they are. I'm also thinking of maybe having a set of questions, and then students I'll do an interview test where I ask you questions and you answer. I'm also thinking of something like that. So still, you're going to have to learn your work in order to answer the questions, that kind of thing. But I don't know. We'll see. We'll see what happens. Let's explore, but if the internet is supposed to help us, but then at the end of the day, it doesn't, we have to come up with another plan to get a mark on the system for you.
All right, ma'am. It's understandable.
Okay. All right.
Sure.
Okay. Any more questions? How come there are fewer students today? Where are the others? Interesting.
Chilling.
Okay. Chilling. Oh, getting data tomorrow. Yes, I heard so. Apparently, and also listen, students, if you don't have laptops, please apply. I sent an email over the weekend. I'm not sure if you guys saw it. So, and please, Zara, put it on the WhatsApp group as well for students that are not getting emails, that they can apply for a laptop, and of course everybody gets data on their cell phones. I wonder if I'm also going to get one since I'm registered for a postdoc. Postgraduate studies. I just wonder, but I don't know. Well, if I get it, whoever wants it can have it. Anyway, so guys, we've come to the end of our lecture. I'll see you on Wednesday.
Okay, thank you, ma'am.
All right. Wait, Zara, before you go, what time is the lecture on Wednesday?
Let me just check quickly.
I think it's at 9:05.
Yes, 9:05.
Perfect. Okay. All right. I'll send an invite just now. Okay. Thank you, guys. Cheers. Bye.
Bye.
Bye-bye.